Now we come to chapter 8. In chapter 8, we shall learn about MELLIN transform. This chapter is divided into 3 modules. We shall start the first module, which is the introduction to MELLIN transform. In the previous chapters, we have learnt about Fourier transform and Laplace transform, and we also know that integral transform is an useful tool in solving ordinary differential equation or partial differential equations. We have seen that in solving partial differential equations, Fourier transform is applied when the space variable is from minus infinity to plus infinity, or if the space variable is from 0 to infinity, Fourier sine or cosine transform may be applied. Also, if the heat equation or wave equation where the time variable occurs, then Laplace transform is suitable for solving boundary value problem or initial value problem involving heat equation or wave equation. But if the partial differential equation is defined in wedge type region, then most suitable integral transform is the MELLIN transform. Here MELLIN transform can be applied to partial differential equations which are defined in wedge type region. So, in module 1 we shall learn about MELLIN transform and how it comes. If one wants to solve the 2-dimensional Laplace equation in an infinite wedge described by r positive, theta lying in the interval minus alpha to plus alpha, where r, theta are plane polar coordinates, then we have to use MELLIN transform. The Laplace equation in r theta coordinate system is given by equation 1, where r is positive and theta lying in the interval minus alpha to plus alpha, and phi is a function of r and theta. There are various methods to solve this partial differential equation. One of the methods is to integrate this partial differential equation given by 1 with respect to r between 0 to infinity after multiplying both sides by r to the power s plus 1, where s is some parameter. That is, we multiply equation 1 on its both sides by r to the power s plus 1 and integrate with respect to r from 0 to infinity. Doing this, we note that first 2 terms of the differential equation given by equation 1 is the integral from 0 to infinity r to the power s plus 1 del 2 phi del r 2 plus 1 by r del phi del r dr. This can be written as integral from 0 to infinity r to the power s del del r of r del phi del r dr. Now, this can be integrated by parts to obtain r to the power s plus 1 del phi del r minus s r to the power s phi r running from 0 and infinity, plus s square integral 0 to infinity phi r theta r to the power s minus 1 dr. If we assume that r to the power s plus 1 del phi del r and r to the power s into phi both tend to 0 as r tend to infinity and r tends to 0, then we obtain integral from 0 to infinity r to the power s plus 1 del 2 phi del r 2 plus 1 by r del phi del r dr. this is equal to S into capital phi S theta, because this term is 0. So, this we are with this term S square into this integral. Now, if we call this integral as capital phi S theta, that is equal to integral from 0 to infinity r to the power s minus 1 small phi r theta dr as given in equation 2, then we get this equation. So, with this simplification, the given partial differential equation 1 reduces to the ordinary differential equation d2 capital phi d theta 2 plus s square capital phi equal to 0, where theta lies in the interval minus alpha to plus alpha as given in equation 3. Now, this ordinary differential can be solved easily if small phi r theta is prescribed on two sides of the wedge, that is theta equal to plus minus alpha, and for simplicity we assume that phi r alpha equal to phi r minus alpha equal to some known function f r. So, that using this condition we solve equation 3 and the solution is given by equation 7, that is capital phi s theta equal to cos s theta by cos s alpha into capital F s, where capital F s is given by r to the power s minus 1 small f r dr, and capital F s is given by capital phi s alpha, which is equal to capital phi s minus alpha, and this equation 5 is obtained from equation 4 after multiplying equation 4 on its both sides by r to the power s plus 1 and integrating with respect to r from 0 to infinity. Thus, the solution of equation 3, that is capital phi, is given by equation 7. Here capital F s in equation 6 is called the MELLIN transform of the function small f r, that is this function, and capital phi s in equation 7 is the MELLIN transform of small phi r. Once we know how to obtain small f r from capital F s, that is if we know the inverse MELLIN transform formula, then small phi r can be obtained from capital phi s theta as given by equation 7. And this provides the solution of two-dimensional Laplace equation in an wedge with prescribed boundary condition given by equation 4. So, using MELLIN transform as we have stated in equation 6, we can solve two-dimensional Laplace equation in an wedge with prescribed boundary condition. So, this gives an introduction why MELLIN transform is needed. Next we come to formal derivation of MELLIN transform and its inverse. The MELLIN transform and its inversion formula can be derived formally from the Fourier integral theorem. If a function small g u satisfies the condition of Fourier integral theorem, then it can be written as g u equal to 1 by 2 pi integral from minus infinity to plus infinity e to the power minus I k u into integral minus infinity to plus infinity gv e to the power ikv dv dk, where u lies in the interval minus infinity to plus infinity as given by equation 8. This is possible to write because of Fourier integral theorem. Now, in equation 8 we substitute x equal to e to the power v and y equal to e to the power u and s equal to c plus ik, where c is a constant. Then u is log y, so that equation 8 can be written as g of log y equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity e to the power minus s minus c log y integral 0 to infinity g log x e to the power s minus c log x dx by x ds. So that we can write it as g log y into y to the power minus c equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity y to the power minus s integral 0 to infinity g log x x to the power minus c into x to the power s minus 1 dx ds as given in equation 9. Now, we define small f(x) equal to g log x into x to the power minus c as defined in equation 10. So, with this definition we can write equation 9 as the left hand side is then f of y and right hand side of equation 9 becomes 1 by 2 pi I integral c minus I infinity to c plus I infinity y to the power minus s into integral 0 to infinity f(x) x to the power s minus 1 dx ds. Now, if we write the inner integral, that is x integral, as capital Fs, that is capital Fs equal to integral from 0 to infinity x to the power s minus 1 small f(x) dx as given in equation 12, then we can write this equation as fy equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity y to the power minus s capital Fs ds as given in equation 11. Now, equation 12 capital Fs, we say that it is MELLIN transform of small f(x) and small fy as given in equation 11 is its inversion formula. So, we can say that number 1, this is a formal procedure to derive MELLIN transform and its inversion. Number 2, the transform parameter S is in general complex as in the case of Laplace transform. And number 3, the significance of real constant C appearing in the inversion formula will be apparent from the theorem we will describe consequently. Now, we shall give in form of a theorem the existence of MELLIN transform and its inverse formula. So, we have learned how to derive MELLIN transform from Fourier integral theorem. Now, we shall establish the existence of MELLIN transform and its inversion formula. Now, we consider the theorem. Let capital Fs be a function of complex variable s equal to sigma plus I tau and it be regular in the strip a less than sigma less than b, and for any arbitrary small positive number eta, let capital Fs tend to 0 uniformly as mod tau tend to infinity. In the strip a plus eta less than equal to sigma less than equal to b minus eta. Let the integral minus infinity to plus infinity capital F sigma plus I tau d tau be absolutely convergent for each sigma for a less than sigma less than b. If we define small fx equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity x to the power minus s capital Fs ds as defined in equation 13 for positive real values of x and fixed c belonging to AB, then in the strip a less than sigma less than b, capital Fs is given by integral from 0 to infinity x to the power s minus 1 fx dx as given in equation 14. This we have to prove. For proof, we note that since capital Fs tend to 0 uniformly as mod tau tends to infinity, in the strip a plus eta less than equal to sigma less than equal to b minus eta, the path of integration in the integral 13, that is in this integral, may be displaced parallel to itself. This means that the integral in equation 13 is independent of the particular choice of the constant c. And we write integral from 0 to infinity x to the power s minus 1 fx dx, this is equal to integral from 0 to 1 x to the power s minus 1 fx dx plus integral from 1 to infinity x to the power s minus 1 fx dx. In the first integral, we choose in the integral representation of 13 for fx c equal to c1 here. Here we shall choose x equal to c equal to c1, and in the second integral we shall choose c equal to c2. Thus, we can write integral from 0 to infinity x to the power s minus 1 fx dx, this is equal to I1 plus I2. So, this is I1 and this is I2, where I1 is the integral from 0 to 1 x to the power s1 into 1 by 2 pi I integral c1 minus I infinity to c1 plus I infinity x to the power minus t capital Ft dt dx as given in equation 13. That means, we have taken I1 as this integral and here we have substituted fx from equation 13 with c equal to c1, and I2 is the integral from 1 to infinity x to the power s minus 1 into 1 by 2 pi I integral from c2 minus I infinity to c2 plus I infinity x to the power minus t capital Ft dt dx as given in equation 17. Here also, as mentioned earlier, I2 is this integral, and here fx is substituted from 13, equation 13 with c equal to c2. Now, we consider mod I1, and that is equal to 1 by 2 pi mod of integral c1 minus I infinity to c1 plus I infinity capital Ft into integral from 0 to 1 x to the power s minus t minus 1 dx dt. This is obtained from equation 16 by taking the modulus value and interchanging the order of integration. So that mod of I1, this is less than equal to 1 by 2 pi integral from minus infinity to plus infinity mod of f of c1 plus I tau 1 d tau 1 into integral from 0 to 1 x to the power sigma minus c1 minus 1 dx after taking the modulus value. Now, as c1 is less than sigma, so sigma minus c1 minus 1 is greater than 1, hence the integral from 0 to 1 x to the power sigma minus c1 minus 1 dx appearing here is convergent. Also, as the integral from minus infinity to plus infinity capital F sigma plus I tau d tau is absolutely convergent for a less sigma less b, the integral minus infinity to plus infinity mod of f c1 plus I tau 1 d tau 1 is convergent. So, we see that this integral is convergent and this integral is convergent. So, that mod of I1 is finite. Hence, we may change the order of integration in I1, so that I1 is equal to 1 by 2 pi I integral from c1 minus I infinity to c1 plus I infinity capital Ft into integral from 0 to 1 x to the power s minus t minus 1 dx dt. And the inner integral, that is x integral, can be evaluated, so that we get I1 as 1 by 2 pi I integral from c1 minus I infinity to c1 plus I infinity capital Ft divided by s minus t dt, and this is equal to, we write 1 by 2 pi I integral over the path capital C1 of capital Ft divided by s minus t dt as given in equation 18. So, this is the line capital C1. Similarly, we can show that capital I2 integral, which was the integral from 1 to infinity, this. Here we have already mentioned that in I2 we have used the representation of small fx from equation 13 with c equal to c2. In a similar manner, we can show that capital I2 is equal to 1 by 2 pi I integral over C2, capital C2, Ft by t minus s dt as given in equation 19, where C2 is the line as shown in figure 1. Thus, with this definition of I1 and I2, we obtain the integral 0 to infinity x to the power s minus 1 fx dx which was equal to I1 plus I2 as given by equation 15. After substituting the value of I1 and I2 from 18 and 19, we obtain this as 1 by 2 pi I integral over C1 ft by t minus s dt plus integral over capital C2 ft by t minus s dt as given in equation 20. Since capital Ft tend to 0 uniformly as imaginary part of t tends to infinity in the strip a less than real part of t less than b, we see that each of the integrals in 18 and 19, these two integrals, tend to 0 as mod tau 1 tends to infinity. Mod tau 1 is the imaginary part of t. Hence, we can replace the two integrals in 20 round a closed contour gamma enclosing S, that is this closed contour. Since capital Ft is regular in the strip a less than real part of t less than b, the only singularity of the integrands in 20, that is Ft by t minus s in the complex t plane, is the simple pole at t equal to s. Therefore, by Cauchy residue theorem of complex variable, the value of integral round this contour gamma is equal to the residue at t equal to s, which is equal to capital Fs. Hence, from 20 we see that integral from 0 to infinity x to the power s minus 1 fx dx is equal to capital Fs. Thus, we have proved from 14 that capital Fs is equal to integral from 0 to infinity x to the power s minus 1 fx dx, which we were supposed to prove. Hence, the theorem is proved. In this module, we have learned the use of MELLIN transform and also the formal derivation of MELLIN transform together with its inversion formula. With this, we conclude chapter 8, module 1.